Right, hello. So this is a shorter talk. I'm just going to focus for a little bit on an interesting problem we faced in the research and education networks about identifying some of the larger traffic flows on our network, the ones that are caused by big science. And by, where do I need to point this? By big science, probably, well, definitely the biggest science project that happens over the RNE networks in terms of data moved between about 170 sites in 40 countries is the science associated with the CERN experiments, the Large Hadron Collider, colliding things, surprise, surprise, and generating an awful lot of data, many, many, many petabytes of data that's moved to lots of different countries and lots of different places where different experiments and algorithms are run against them. As part of that, we need to enable an infrastructure to get that data there. That's where this worldwide Large Hadron Collider computing grid, which is the infrastructure, has research networking teams, which I take part in. These are the people that have been involved with the Scitag work I'm just about to talk about. We also do other things that are to try and help improve the way things move around the network. So new TCP versions like BBR, we're very interested in that, have been testing that. Much better performance when there's loss in the network, which unfortunately inevitably does happen. Jumbo frames, so we're back to the MTU topic, using 9,000 MTU internationally, which was where packet too big filtering can be a problem. I'm looking for one person in the room that's had problems with that, but won't look at them for too long. And you know, as engineering design team, if you like, we think we're doing things that help make things perform better. But when they perform better, we still need to know what the traffic is. So the problem, if you like, is that in these NREN, the National Research and Education networks, we do carry a lot of science traffic, way more than you might think, but we don't necessarily understand it as the operator, nor do necessarily the science experiments themselves have much of an idea of where their traffic is going or why in some cases. So being able to see traffic in the network or understand the flows in the network, know which experiment it's associated with, whether it's one of the CERN ones or something else, and what type of activity it is. Is it just a general data transfer? Is it some kind of backup thing? What's the activity behind the reason the data is being moved around? And we can also look, if we can understand what the traffic is, about making more efficient use of the network as a result of that. We can also look at performance measurements. So if you understand the flows, the throughput, the time taken, etc., we can see how the end-to-end performance is working and maybe focus on areas where it could be improved. There's all sorts of things that we can do. Another thing for RNE networks is having a lot of transatlantic links, for example, and understanding the accounting of who's using it and for what. You might think, well, you just look at the network flows, it's easy. But actually, if you're looking at just net flows with a source and destination IP and ports, as a network operator, you have no idea what that is. Without going to the site, asking, well, which systems have these IPs and what applications are they running? You don't have that. So we really could use a way of better understanding it. And there are some overlay networks, layer 3 VPNs we use, but again, those can be used by multiple experiments, so they don't necessarily drill down. So the solution that the research networking team came up with was Scitags. And Scitags is a scheme that allows you to tag traffic or flows with both an experimental ID and an activity ID. And there's two different flavors of this. One is packet marking, which is encoding that information, the metadata, if you like, directly in each packet, which is something that you can do with IPv6 because you can do it with the flow label, come on to that in a moment, or, I've missed it there, hop by hop or destination option. And that's v6 only. So per packet tagging is something you can only really do, I'll say simply, but I'll come on to that. It's something you can really only do with v6. Or by flow marking, and our initial approach was simply to send a UDP message from the source to the destination or to a collector at the start of a flow and at an end of a flow, what we call fireflies. And that works for v4, v6 because it's just a UDP packet. So we had these two approaches we came up with, one IP version independent just for the flows and the other v6 only for per packet marking. And once you have those things, then you can do this tracking correlation, you can get all the insights. Who's involved with this? At this stage, it's a number of the NRENs, including us at Jisc. It's various universities and science organizations that are taking part in the experiments on the right there. Atlas, CMS, LHCb, Alice, those are the big 4 CERN experiments. And then there's various people that develop the tools that allow all the data to be pushed around. Rusio is a sort of an intent-based system for saying what you want to happen. Then FTS makes it happen and schedules the transfers, and tools like XRootD move the data. And something I haven't said here is that this environment, particularly the CERN one, we have Dave Kelsey in the room. He's been chairing a working group that for many years, not quite 30, but many years, has been pushing this whole infrastructure to work with V6, and ultimately V6 only, and now well over 90% of all the traffic in this infrastructure is V6, so it's a big success story, and there have been talks at this in the past that you can go back and look at this event. So what does this look like in terms of the data transfers and how those relate to the per packet and per flow marking? We have these tools, the Rusio and FTS and XRootD on the left as the request to transfer are passed down the stack, if you like, and XRootD moves the data. XRootD has the support for both of these, come on to that in a moment. So you can either send the fireflies at the start and the end, or even during the flow if you want to, or you can do the per packet tagging. And then the fireflies can either be sent to the destination and or a collector where you can collect all the firefly information, then present it via a visualization, or you can just look at the packets in flight. More of that in a moment. The per flow marking, that's where the initial focus has been on, because it works with V4, V6, it's a little easier. That's now widely deployed within the WLCG. About 25% of the flows now have the fireflies enabled on them by the end systems that are sending them. That number is growing quite rapidly. So across all the experiments and all the different sites and all the different software, it's looking to be in a very good position. And what we're now looking at are other science projects that can take this on. So the Square Kilometre Array is a big science experiment with lots of radio telescopes in South Africa and Australia. Vera Rubin, you might have seen in the summer, these fantastic images from deep space coming in, amazing images. They're using the same tooling as WLCG. So we can use these tools for that science that you just see on the TV, but it's obviously very important science. Firefly coverage, it's just, this slide just points that it's worldwide, the sites that are sending these firefly information. And there's a link there you can look at later from the slide deck. That's an example of the sort of visualizations you can see then, and you can understand what experiments, what activities, what sites, whether it's V4 or V6, all these sort of analysis and visualizations for the NRENs and the science people that can see that. The thing that's more interesting perhaps to people in this room, because it's V6 only, is that you can do per packet marking. That's a big advantage that you get with V6. And there's 2 ways, we talked about it for quite some time, and there were basically 2 ways you could do this. One is to use the 20-bit flow label in V6, because it's 20 bits, so you can put bits into those 20 bits and send them. And we came up with this scheme for having 9 bits of that to identify the experiment, 6 bits for the activity, and then 5 bits for entropy, because the flow label can be used for entropy in hashing and other things. And we wrote an internet draft about that. It was reasonably well, we didn't get things thrown at us in the ITF when we presented it. There were some people we thought might, and they were actually saying, oh, this is a cool thing you've done. It's actually interesting to see the write-up of why you did it and so on. But there were the people that quite reasonably pointed out that the IPv6 spec 8200 says, well, the drafts actually, or the RSCs related to that, says you should not or must not put semantics into the flow label. So there was some pushback on publishing that as an RFC because it's not something you should strictly do. Interest that you can do it and it works internationally, great, but yeah, don't do that. And the pushback was to do, well, what you should do is use an extension header, either a hop by hop or a destination option. There's arguments for using one or the other, and insert that in every single packet, and then obviously be careful if you're inserting extension headers that you don't cause MTU problems. There is more of a performance penalty in doing this. Just writing a value into the flow label is fairly straightforward. Actually inserting a header, you've got the overhead then in the transmission that you're using some of the data space that could be used for data with extension headers, and you've got the little CPU hit of doing the insertion of the header. And this is where we've got this lovely tool called Floaty, written by Pablo Soto. He's developed this. We're now using it, testing with it, both for fireflies and the header insertion. It's basically a library that allows us to do all that. It uses eBPF, so it's sort of free entry to the kernel, if you like. You can think of it that way. And you can run that as a container or a package on the systems and use it, if you're running it on one of the systems that's sending the files, to send either the fireflies or do the per packet extension header insertion. And that's what we're using. I don't know that, at the end of the slide deck, there's a link to the source if you want to go and see how we're doing it. Some details of the implementation. The current implementation for the extension headers is only using 8 bytes, so it's not a particularly big overhead in terms of the amount of data you're using, particularly when you've got 9,000 MTU. We've got it set so you can use hop-by-hop and/or destination options, so you can choose which or both you want to use. In terms of the overflow potential for MTU, one way around that is just to use MSS to clamp it down so that if you're at 9,000, you actually run such that you're allowing for the extension headers for when you're using xrootd or if you're doing tests with iPerf, whatever it happens to be. At the moment, the encoded data is only 3 bytes, the experiment and activity, so that's padded to 4. You could also insert, I think I mentioned that in the last slide, you could put additional information in there, obviously at the cost of stealing more data from more space from the real data. Certainly in the fireflies, you can put TCP/IP stack information, which version, which TCP version you're using, what are the buffer sizes, how is the TCP configured, and then learn a lot more from how the flows are performing against how the system is tuned, buffer space, etc. What else to say? There's a lot of optimization there to minimize the performance impact of doing this insertion. And generally what we've seen is it's something like a 5 or 6% performance hit on doing it, so it's not too bad. Right, what's happening at the moment? So this method, using this FlowD implementation with eBPF, inserting, either rewriting the flow label or inserting extension headers. It was tested at the big science event that happens every year, supercomputing. Last year, SE24, we're getting about 200 gig throughput doing this. This year, it's happening this week. Right now, supercomputing 25 is happening, and the guys are over there, and they're trying to demonstrate this now at up to 1.2 terabits on 3 400 gig data transfer nodes using this software with the eBPF. And they're quite optimistic from pre-testing they've done that they can make that work. So it's demonstrating it working at the very high rates that we need for these big science experiments. As the Large Hadron Collider goes to its next generation, if you like, at the end of the, what decade are we in? At the end of the 20s, the data rates are going to jump significantly. So actually having these things working at those rates will be a minimum requirement. We're also talking to more sites about adopting these tools and using these tools, the fireflies and/or per packet marking. One of the challenges with the per packet marking is finding ways you can export the information that's in the extension headers. That's proving to be a bit more tricky, is seeing it on path and dealing with that. What we are doing in the R&E space, we can use programmable devices, using things like P4, and you can just have a very performant programmable device in line that can actually pull that data out and report it at line speed. Testing extension header transparency, that's very important. You may have seen reports of extension headers being dropped. That's something that is a problem, less so we think in the R&E networks. But what we're planning to do to see whether inserting the extension headers causes failure in the transmission is to use the sort of common tools we use for network performance in R&E networks, perf sonar being a nice free example. There's a link there. And we can simply run a FlowD container on a perf sonar node, and where it's normally just doing throughput, loss, and latency measurements, it can do those while inserting the extension headers, and we'll see whether those tests work or not. And that will tell us whether the extension headers are causing drops or not. And then the last thing here, I suspect Nick Baraglio might talk a bit about this. I think he's on this afternoon with his IETF update. There's been a revisit in the IETF 6-man working group about extension header processing. And there's sort of, there are people that are a little bit apart on this, shall we say. Basically, the question is, are extension headers usable? Has it been a mistake defining extension headers for v6? And one extreme view is, well, there's only, perhaps all we should do is just allow one hop-by-hop option and just completely disable destination option headers because they're not useful to anybody. The other end of the spectrum are people saying, well, we're only a small number of years into production v6 deployment using these things. It would be crazy now to disable that future capability for the next 30 years. That's kind of the end of the spectrum I'm on. And we have a number of RFCs that state how these extension headers should be handled now, and that hop-by-hop processing, even if you can't recognize headers, just forward them anyway. Don't be worried by the limitations that may be on the devices. So a more controversial draft has failed at ISG review, which is the bit where all the very wise heads look at drafts before they get published, because that was being very prescriptive about the maximum size of header chains and how you filter them and what you should allow and not allow. So that's an ongoing debate. So those are the things that are happening. And then there's just a few links there in the slides you can look at to go other places and find out more. Thank you.